present our work on tactile odometry and aerial physical interaction. In this work, we propose a novel approach for odometry estimation for aerial robots by extracting information from contact with unknown environments. Akin to conventional pose estimation methods in wheeled robotics, we utilize a rolling antefactor to provide odometry for aerial robots while in contact. Conventionally, aerial robots estimate their pose relative to objects in their environment using a combination of onboard visual sensors and exteroceptive position sensors, such as GNSS. However, these sensors experience limitations in some environments of interest. For example, in underground exploration tasks, GNSS signals are not available, and the surroundings can inhibit the camera's performance through limited illumination, smoke, or dust. Additionally, in close proximity scenarios, the camera's field of view is often insufficient to capture enough stable features. In nature, myriad instances of navigation exist, often also independent of visual cues. Instead, creatures, including humans, adeptly navigate their surroundings by feeling the environment. Drawing inspiration from these natural models, we integrate tactile odometry into aerial robots, offering a robust alternative for state estimation in their navigation. We equip a conventional quadrotor with a sensing antefactor that embodies compliance and odometry estimation in one design. The antefactor measures the displacement of a linear and a revolute compliance using encoders. A laser optical trackball at the contact interface allows low friction sliding while measuring the distance traveled while in contact. An IMU provides the current heading of the antefactor while sliding. Initially, the UAV is commanded to fly forward until contact with the environment is detected in the compliant joints. Afterward, it aligns with the environment by moving on a circular arc centered at the contact point until the passive revolute joint is brought into a dead band close to zero. The UAV then continues to follow a trajectory pre-computed in the surface reference frame, such as a straight line or a sine curve. Before executing, it is transformed into the world reference frame using the UAV's aligned orientation. By utilizing the antefactor's heading and the distance measurements from the trackballs, we propose a dead reckoning approach to estimate the position of the antefactor relative to the initial contact point. The UAV's pose is then derived directly from the inverse kinematics of the antefactor in conjunction with data from the onboard IMU. In a total of 32 flight experiments, the system proves the efficacy of tactile odometry with various differently oriented environments, as well as for different kinds of trajectories while in contact. After calibration, the 90th percentile of the odometry error in direction of motion, the on-track error, and the orthogonal component, the off-track error, stay within 10 and 2.5% of the traveled distance respectively. The system is able to align with angles up to 15 degrees and provides a position estimate and yaw estimate in 90% of the contact time. The Euclidean position estimate error stays within 5% of the traveled distance in all trials, and the yaw estimate error standard deviation remains below 5 degrees. Overall, this work provides a valuable alternative solution to the odometry problem for aerial robots where conventional state estimation approaches, for example vision-based or GNSS-based, cannot be exploited. Such approach paves the way to robust and lightweight aerial tactile navigation in challenging environments for emerging applications. The proposed approach is particularly suited for aerial interaction tasks where contact is desired. The contact-based odometry provides feedback directly in the task space, enabling more precise antefactor control. Future work in this direction will look into increasing the nominal accuracy by improving the hardware components and closing the loop from contact-based odometry estimation to contact-based flight control.